Hello my dears, how are you all? So what we studied in the last class? We discussed about the concept of hysteresis and iron losses, right? And we did some equation for, or derived some equation for the hysteresis loss as well as the eddy current loss formula and its connection with the frequency. And we did some derivation, right? Some relation for eddy current as well as hysteresis loss, like pH directly proportional to V1 square and PE directly proportional to V1 square, and hysteresis loss PS directly proportional to V1 raised to x into F raised to 1 minus x. That relation also we derived, right? So today we are going to discuss the another important loss in the transformer, which is nothing but the copper loss or variable loss. Copper loss or variable loss, because these losses are varying with respect to the load. That's why it's called the variable loss. While the iron loss is a constant loss, it's constant for all the loads, because in equation itself, the iron loss equation hysteresis or either hysteresis or eddy current. You can't see any term with connecting the load, right? Whether it is load current or load percentage load or fraction of load, you can't see anything there because it is independent of the load. It is a constant loss actually. But in the case of copper losses, it is dependent upon the load current. That is why it is called the variable loss. So whenever we vary the load, the loss is also varying in nature. That's why the term variable loss or copper loss. So transformer, you can see the transformer having a primary winding as well as the secondary winding, right? Primary winding as well as the secondary winding. Primary winding is nothing but we are giving supply. The winding at which we are giving supply is called the primary winding, and secondary winding is nothing but the load which is connected across the winding. That winding is called the secondary winding. Am I right? So wherever we connect some load across the secondary winding, there will be a flow of current I2 in the secondary. You know that, sir. There is a flow of current I2 in the secondary. Of course, there is a draw of current I1 in the primary also. Okay. So due to the primary current I1, you know the equivalent resistance of a transformer. You did that in the last class, that there is a primary resistance, primary reactance, secondary resistance, secondary reactance. So primary resistance, whenever there is a flow of current through the primary resistance, there is a drop. So the total copper loss will be equal to PC will be equal to, I can write like I1 square R1 plus I2 square R2, where R1 and R2 are nothing but the resistance in the primary side and the resistance in the secondary side, because copper losses are predominantly due to the loss in the resistor. Okay, loss in the resistor. So I1 square R1 plus I2 square R2. Am I right? That means, and also we have the equation I1 by I2 is equal to, what is that? N2 by N1. Correct? I1 by I2 is equal to N2 by N1. So I can write like PC is equal to, this I1 can be write like N2 by N1 I2 square, correct? I2 square plus I2 square R2. Am I right? Or I can write like I2 square, if I take common, I2 square divided by N2 by, correct, right? I1 square into R1 is there, right? R1 into R1, correct, R1 plus I2 square R2, correct? Because N2 by N1 the whole square into I2 square is nothing but I1, right? N2 by N1 the whole square into I2 square is nothing but I1 square. So this I1 square can be replaced like N2 by N1 the whole square into I2 square, correct? Into R1 plus I2 square R2. So if I take I2 square as outside as common, will become N2 by N1 the whole square, right? R1 plus, what is that? R2. So it is nothing but I2 square into, what is N1 by N2 the whole square R1 plus R2. See, R2 is the secondary resistance. N2 by N1 the whole square into R1 is nothing but what? R equivalent to, right? It is the resistance referred to secondary. Total resistance referred to secondary. You know this, right? That is R2 plus R1 into N2 by N1 the whole square is nothing but R equivalent to which is nothing but equivalent resistance referred to what? Secondary side. Equivalent resistance referred to secondary side. So copper loss is equal to, or you can same thing, if you convert this for I2 is equal to what? I2 will be equal to N1 by N2 into I1. You can use that equation also. Instead you troubled I1, you can trouble I2 also. You can derive the same equation and you will reach another equation for PC, which is nothing but I1 square into RE1, same manner. Or we can write like PC will be generally equal to I1 square into RE1 equal to I2 square into RE2. Both cases it is same. So the copper loss or full load copper loss, right? Any copper loss, the copper loss will be written like I1 square into RE1 either or I2 square into RE2. If you considering the secondary terminal, you should take care of the secondary current and secondary equivalent resistance. If you take care, or if you considering for the primary side, you should take care of the primary current as well as the what? Primary equivalent resistance. That's the only difference. That is the only difference. Okay. And next losses in a transformer is nothing but stray losses. Stray losses. Stray losses. Okay. So see, the stray losses is nothing but, see, this is a core of a transformer. This is a general simple figure. It is a core of a transformer in which the primary winding is wound here, secondary winding is wound here, right? So if you apply some current here, there will be flux in the what? Core. Definitely there will be flux in the core. This whole transformer is covered with a tank. The whole transformer is covered with what, my dears? Tank. So if the flux is changing in the primary, I mean if the current changing in the primary produce a variable flux in the circuit, that flux is linked with the, actually for self-induced EMF, the flux should be linked with what? This conductor only, right? This conductor only, right? But due to the effect of what? Magnetic flux, the flux may not link exactly through these conductors only. This may link, a part of the flux may link to the tank also, to the outer covering also, to other conductors in the circuit also, It may be the connection wires or the external terminal, anything. It may be linked to that side also. Mainly it may link to the tank of the transformer. Tank of the transformer. So at that time, there is a chance of producing eddy currents in the tank. And finally, that will lead to a lot of heat. Not actually very high, a small amount of heat. Not a lot of, a small amount of heat in the tank. So if you touch the tank of a transformer, you will always feel some heat. A part of the heat is due to the stray losses. But comparing to the copper losses and iron losses, this stray losses is very, very less or very feeble in nature, very weak. So it may be sometimes it is neglected. Not sometimes, all the time it may be neglected. No issues will arise in the calculation because it's that much small value, So the stray losses are nothing but it is due to the eddy current in the conductors as well as the tank. Conductor in the sense, not the winding conductor, but other conductors. Clear? So that's all about the stray losses. Next loss is nothing but insulation loss or insulating loss. So these are the losses in the what? In the insulating material in a transformer. For example, we know that in the transformer there is high voltage winding as well as low voltage winding. In the core transformer, suppose you take for the core type of transformer, there is high voltage winding as well as low voltage winding, right? So in between these there is a what? Paper or insulation. In between this there is this is LV and this is HV. In between this there is a what? Insulation, paper insulation, right? In between this there is a paper insulation. That's an insulator, right? That's an insulator. But no material in the universe is a perfect insulator. Even vacuum can conduct electricity at very, very high temperature and certain other conditions. So we can't say that the paper is a perfect insulator. So there is always some leakage current through this paper, and there is loss of current through that type, that insulator also. So that is the loss of energy in other words, right? That is the loss of energy in other words. Or except, along with this loss, there is another type of loss due to the insulation, which is nothing but this winding, the whole winding is immersed in a transformer oil. Both the primary winding as well as secondary winding is surrounded by a transformer oil. You know that. So transformer oil is a perfect insulator, not a perfect insulator. It's also insulation property is there, but not a perfect insulator. So that also allows some leakage current. So there is also some loss. So the losses due to the leakage currents in the insulating material, whether it's in the paper insulator, in between the windings, or the transformer oil in the tank, in the transformer tank. Okay, anything. So there will be a chance of losses. That type of losses is named as insulating losses. But the combined stray losses plus insulating losses are very, very small in value compared to the copper losses and iron losses. So normally it is neglected. Is it clear? So and see, very high volume transformer, very high volume transformer. So high volume transformer means there is a reasonable amount of current, there is a reasonable amount of leakage current, there is a reasonable amount of oil also. So that type of transformer, in that type of transformer only we can consider a small portion as the stray losses and insulating losses. Other type of transformer, normally we are using normal transformer, simply we can neglect that type of losses. Okay, so that is the different type of losses in the transformer. And we have to see next. Separation of hysteresis and eddy current loss. Separation of hysteresis and eddy current losses. Very, very, very important. Very, very important concept. Very, very important concept. Separation of hysteresis and eddy current losses. What is the need of separating hysteresis and eddy current loss? Because you know that in a hysteresis losses, you can't directly measure hysteresis loss, right? You can't directly measure. Because it contains some constant value also, some constant. And in the eddy current loss, hysteresis loss, you may see F1 raised to X, right? F1 raised to X. So, that X value may vary from 1 to 2, but you can't exactly say what is the value. You can't say exactly what is the value. So you have to separate that eddy current and hysteresis. Combinedly you will get as an iron loss, Combinedly you will get an iron loss, but the separation is needed. If we need to separate that hysteresis and eddy current, we have to use this technique in order to separate the hysteresis and eddy current. Okay. So first of all, you may get a total loss. But as an iron loss you may get, but the separation is difficult. So this technique is used to separate the iron loss. Okay. So how can we separate that? Let's see. See, we have the equation of hysteresis loss. We have pH, that is the hysteresis loss, is directly proportional to what? F. Or I can write like pH directly proportional to AF. Sorry, equal to AF. If you remove that proportionality constant and introduce a constant which is nothing but AF. Okay, that be equation number 1. And eddy current loss, directly proportional to F square. And if I remove that proportionality constant, it will become B into F square. That be equation number 2. So the total iron loss Pi will be equal to pH plus Pe, right? pH plus Pe, which is nothing but AF plus B into F square, right? AF square B into F square. Let be okay. So what is Pi by F now? Pi by F now, which is equal to A plus BF. A plus BF, very very important relation. Pi by F is equal to A plus BF. Okay. So if you draw this equation as a graph, it will be like, see what is the similarity, right? It will be y is equal to mx, or simply y is equal to c plus mx, right? Y is equal to c plus mx format, right? Y is equal to, y is nothing but Py by F. Y is equal to c constant plus m into f, right? M into x. So what is the x coordinate here? X coordinate is nothing but f. What is the y coordinate here? Y is nothing but Pi by f. So if you draw the graph between f versus Pi by f, you will get a graph like this. And this point is nothing but A. This point is nothing but A. Because A is nothing but the y-intercept. A is nothing but y-intercept. Okay. And B is nothing but the slope. B is nothing but slope. So A is nothing but y-intercept and B is nothing but, my dears, slope of this graph. So if you know this A and B, you can find the iron loss for any frequency, okay. When we are doing problem, it will be very clear to you. So this is the procedure. First you just need to draw, or you need to take Pi by F as one coordinate, F as other coordinate. Simply draw the graph between these two, and slope will give the value B, and the y-intercept will give the value of A. So if you know the value of A and B, then it is very easy to find the iron losses at any frequency, or core loss at any frequency. Okay. So that is how we have to separate this iron loss as well as hysteresis loss as well as the eddy current loss. Okay. So we can write a problem. So through problem we will learn more about this concept. Okay. Through problem we will learn more about this concept. Okay. So write a question. In a transformer, the core loss is 100 watt at 40 hertz, comma 72 watt at 30 hertz. Find the hysteresis and eddy current loss. Find the hysteresis and eddy current loss. So this is our question. See, this is our question. So what was our aim? In order to separate the hysteresis and eddy current loss, because company you will give a value of iron loss, you may find in any phase as value of iron loss, but you have to separate that too, right? So you have to separate that too, right? So see, what is the question? In a transformer, the core loss is 100 watt at 40 hertz, right? So I can say a Pi is equal to, Pi1 is equal to what? 100. And at F1 is equal to what? 40. Pi2 is nothing but what? Pi2 is nothing but what? 72 watt. 72 watt, right? 72, you can write like watt, okay. At F2 is equal to what? F2 is equal to 30. We have to find the hysteresis and eddy current loss for at 50 hertz, right? 50 and AC current loss at 50 hertz, right? At 50 hertz. So you have to find Pi3 at F3 is equal to what? 50 hertz. This is the question. This is the question. The question is clear to you? The question is clear to you, my dears? So you have to find what? Pi3 at 50 hertz. Let's see that. if you have Pi, so I can write like Pi by F is equal to, what is the format? Pi by F will be equal to A plus B, right? So Pi by F is equal to A plus B you have. So first case 100 by 40 equal to what? A plus B into 40, correct? And next case what? 72 by 30 equal to what, my dears? It is also again A plus 30, correct? So let be equation number 1 and let be equation number 2. So you can reduce this equation, so it will become 2.5. Am I correct? 5 by 2 is 2.5. If you reduce this, you will get what? 36 by 15, right? So it will become 15 into 2 will be 30, 15 into 4 will be what? 60, right? So 36 by 15 will be 2.4. So you have one equation like this and two equations like this. I am going to subtract this 1 and 2. I am going to subtract this 1 and 2. What I get? 2.5 minus 2.4, which is equal to what? 0.1, correct? 2.5 minus 4.4 is nothing but 0.1, which is equal to A minus A, it will cancel. B40 minus B30, what is that? B10 or 10B, or B is nothing but 0.1 by 10, my dears. So it will be nothing but B is equal to 0.01. B is equal to 0.01. Is it clear? Is it clear, my dears? Did you get that? So you got the value of B, right? So you have to find A also. So substitute in any of the equation. Let I put here, substitute in equation number 1. Equation 1, what I get? 2.5 will be equal to, what is that better? A plus 40 into 0.01 is nothing but 1 by 100, correct? 0.01, no? 2.5 is equal to A plus B into 40, right? So A plus B is nothing but 1 by 100 into 40. Okay, so it will be cancelled and I will get, right, 2.5 is equal to A plus 4 by 10 is nothing but 2 by 5. 2 by 5 is nothing but what? 2 by 5 is nothing but what? 0.4, right? So A will be of course 2.1. A will be of course what? 2.1. So now you got the value of A and B, right? Now you have the value of A and B. So we have to find what? Pi3, right? So Pi3 is nothing but, my dears, Pi3 is nothing but, again it will be in the format of A plus BF, right? AF plus BF square, right? Pi3 is nothing but, find the hysteresis and eddy current loss at 50 Hz now. So you have to separately calculate. Okay, I am ready. That also I am ready. So hysteresis loss. Now hysteresis loss at 50 Hz. Okay, first you have to find that. So the equation of hysteresis loss is nothing but pH will be equal to what? pH will be equal to A into F, correct? pH will be equal to what? A into F. So it will become, what is the value of A now? 2.1 into F is now, F is nothing but 50, right? So 2.1 into 50, right? So 21 into 5 will be equal to 5 and so it will become 105 watt. So you got the value of hysteresis at 50 Hz. Next you have to find eddy current. Eddy current loss at 50 Hz. So what is the equation for eddy current loss, my dears? What is the equation for eddy current loss? Eddy current loss is nothing but PE equal to B into F square, right? B into F square. So you know the value of B, right? You know the value of B now. B is nothing but 0.01, correct? B is nothing but 0.01 into 50 square. 25 square, 50 square is nothing but 2500. So this 00 and this 0.01 is nothing but 1 by 100 and 2500. So we cancel simply 25 watt. Simply 25 watt. So you will get what? pH will be 105 and PE will be 25 watt, right? 25 watt. Correct? Did you get that? Did you get that, my dears? So this is the hysteresis and eddy current loss. And if you want to find the total iron loss now, total iron loss, it is in the question, it's not. In the question, it's not need to find the iron loss, total iron loss, but we can find that also. Total iron loss will be equal to, what is, my dears? Pi will be equal to what? AF plus, what is that? BF square, correct? EAF plus BF square. So what is the AF value? 105. What is the BF square value? 25. So it will become 130 what? So that is Pi. So the total iron loss will be equal to what, my dears? It is 130 watt, right? It's 130 watt. 130 watts. Okay. So that's all about the question. That's all about the question. So that's all about the question. Okay. Did you get the idea? Did you get the idea? If you have any doubt, you can comment. Okay. If you have any doubt, my dears, you can comment. If you have any shortcut method rather than this, you can also comment, right? You can comment that also, no issues. If you have any excellent method than this, you can comment that also. So next you have to see very, very important topic in transformers, which is nothing but OC test or open circuit test. Open circuit test, or sometimes it's called simply what? OC test. OC test. OC test in a transformer. OC test in a transformer. So what is the purpose of doing the OC and SC test is nothing but in order to, these tests are used to find the equivalent circuit of a transformer or the parameter of a transformer. Parameter of the transformer includes what? R omega or RW, XM, R1, X1, right? Or R equivalent 1, X equivalent 1, IW, IM, I0. You see, these are the parameters in the transformer equivalent circuit. So, open circuit test normally used to find these parameters, not fully. Open circuit gives some parameter and short circuit test give other type of parameter. I mean, combinedly, this open circuit and closed circuit test will give you the full parameter of the transformer. So let's see first what is the open circuit test or OC test. What is open circuit test or OC test? Okay. Listen very carefully. See, so open circuit test, for performing open circuit test, we have a wattmeter, MLCV, right? MLCV, a wattmeter. You already did in the laboratory, you know. You already did this in third, I think, a third sem or fourth sem. In measurements, like measurement subject, you know. Regarding that measurement subject, I think you already did this. Measurement laboratory, right? Measurement laboratory. So, there is a wattmeter, there is a voltmeter and ammeter. So the arrangement may be like this, arrangement will be like this. The peculiarity of the test is the LV side we have to connect all the equipments and the HV side kept open. and the HP side kept up. First we have to see why we have to open high voltage side and we have to connect all the equipments in LV side. Suppose imagine, so it is a 11 bar, so simply what, 230 or 460 volt transformer, okay, 230 or 460 volt, or simply a super values we can take, a 115 volt 230 volt, imagine, okay, it's a transformer, LV is 115 and output or high voltage are 230. Why we have to connect all the parameters in LV side and HP open for doing this test is that for LV side, see LV side, no, first of all this value of the voltmeter, wattmeter and ammeter will be very less if you done this test on LV side. If you done the same test on HP side, you need to buy or you need to connect a larger rating wattmeter, voltmeter, ammeter, etc. Clear? So that is the main reason for doing this OC test on LV side, that means low voltage side, and keep opening the HV side, keep open the HV side, okay, that is the main purpose. So what is the test? How can we do this test? So connections are made as shown in the figure. We have to slowly increase our voltmeter, or supply, simply supply. This V1 and V1 is approximately nearly equal. A small change will be there, that is to the wattmeter, but except that these and these are equal, simply represent V1 as V1, here also V1, okay. So see, if you increase the voltage here, and increase the voltage up to the rated voltage in the LV side. Suppose you take 115 as the 115 by 230, you have to make it increasing up to 115 volt. That means you have to apply rated voltage on the LV side bus. You have to apply what? Rated voltage on the LV side. That is the first thing. Note down the value of voltage at that voltage, let be V1, and note down the value of current, which is nothing but I0, where I0 is nothing but what? No load current. My dear, what? It is no load current. So you simply measure no load voltage and no load current. You can measure this wattmeter results, okay, which is nothing but no load loss, okay, no load loss, bus. That's all about this no load test. The experiment is bus, and later it's a calculation, okay. So we have, see, W0 is nothing but, I can say like W0 is nothing but V1 into I0 cos phi 0. Am I correct? V1 into I0 cos phi 0. From this you can calculate the value of cos phi 0. Am I correct? Cos phi 0 is nothing but W0 divided by V1 into I0. Cos phi 0 is nothing but W0 divided by V1 into I0. So the another aim of doing this open circuit test in order to find the open circuit or no load power factor. Cos phi 0 you got. Okay, first step is that you got the value of cos phi 0. If you got the value of cos phi 0, what is IW? IW is nothing but, my dears, I0 cos phi 0, correct? You will get that value, right? And what is IM? IM is nothing but I0 sin phi 0, or you can simply what? IM will be equal to what? I0 square minus IW square. Simple, you can do that also. Because I0 is nothing but IW plus IM vectorically. These all are phasor, no? That is why. So the magnitude of IM will be equal to root of I0 square minus IW square. So now you have the value of this IM and IW. So what will be RW? What will be RW, my dears? What will be RW? RW is nothing but, what is that? V1 divided by, see, in the transformer equivalent circuit, did you remember that? Did you remember the transformer equivalent circuit, my dears? This is the transformer equivalent circuit, right? So this is nothing but IW and this is nothing but IM. This is RW and this is J into XM, right? J into XM, correct? And you applied a voltage here, that is nothing but V1. So what is the value of RW is, which is nothing but R equal to V by I, right? V by I. So it is V1 by I omega. And XM is nothing but, my dears, it is simply V1 divided by IM plus. So see how many parameters you got. How many parameters you got, my dears? How many parameters you got from the open circuit test? Simple test itself, you got how many parameters? You got IW, you got IM, you got RW, you got XM, and you got no load power factor also. You got no load power factor also. So this is the way which you have to do. You have to proceed. So no load is the value of no load. I mean the no load test used to find the iron loss, right? This value of what W0 is nothing but the no load loss. No load loss is predominantly due to two component, no load copper loss plus no load iron loss, right? No load iron loss, correct? I will explain that. No load loss is actually equal to what W0, which is nothing but no load copper loss, right? No load copper loss plus no load iron loss. No load iron loss. I already told you that this iron loss is independent of the load. So simply you can use simple iron loss only. And the value of this I0 is very, very small. And a portion of this I0 is what? Dissipated heat in the form of what? IW square into RW. IW square into RW. That is called the what? No load copper loss. No load copper loss. And this value of I0 is again small. And this IW is again small. So the no load copper loss will be very, very small. Very, very small. And the wattmeter D reading predominantly gives the iron loss. It's very, very important. So in a one word question, in your examination, in a one word question, you may expect a question like this. The no load test or OC test in a transformer gives these options: copper loss, iron loss, hysteresis, anything. Okay. The answer is iron loss. The answer is iron loss. So I can conclude like OC test gives iron loss. Very, very important, my dears. Very, very, very important. Of course, you will get the parameters. Of course, you will get the parameter. But the main thing is that you will get the iron loss. You will get the iron loss. So the W0 is nothing but the iron loss. You may feel that, array, wattmeter is actually measuring the active power, right? So iron loss, how can it measure? The reason is I0 is very small. IW is again small. So IW square into R omega, it's very, very small. So the rest of the power is actually what? IW square into R omega is the actually power measured by the wattmeter. But this wattmeter again reading so much. Again reading in so much. What is the power actually? So this reading is due to what? This reading is due to the iron loss. That reading is due to, my dears, it is due to the iron loss. It is due to the iron loss. Is it clear? Is it clear, my dears? So that is the main purpose of doing OC test. Okay? So that's all about the OC test. And next we have to see SC test. We have to see short circuit test. Next we have to see short circuit test. Very, very important test, my dears. These are very, very important tests. These are very, very important tests in transformers. You may expect definitely one question, sure short question from this. You may expect. You may expect. Next we have to see short circuit test. Or I can say like simply SSC test, right? Yes, simply SSC test, short circuit test. So draw the figure. Listen my dears, this is a circuit diagram for performing the short circuit test. Did you feel any change? Did you feel any difference with respect to the previous test? Did you see any difference? Carefully observe. Did you see any difference here? Did you see any difference here? What is the difference? What is the difference here? What is the difference here, my dears? The difference is that, my dears, here in the short circuit test, we connected all the equipments. We connect all our equipment or measuring devices in the HV side. Simply we short circuited the LV side. Simply we short circuited the LV side. What is the reason? What is the reason? In case of open circuit test, we have to perform the test for rated voltage. So rated voltage regarding high voltage side is very difficult, but rated voltage regarding LV side is very easy. That means the measuring devices regarding the LV side is very easy. That's why we connected all devices in LV side and we apply the rated LV voltage. But here in the SC test, it is short circuiting means nothing, my dears. It is a full load condition. That is a no load condition. Short circuiting means it's a full load condition. It's a full load condition. So for full load condition, of course there will be maximum current flowing in the primary side, right? Primary side. Maximum current will be flowing in the primary side. So the purpose of doing this test is nothing but, I will explain that. So the main important point here is that we have to apply certain voltage and we have to make the current as rated. That means you have to apply the rated current for this test. You have to apply the rated current for this test. So if you take LV side rated current, the current in the LV will be higher than that of the HV side. That means the transformation ratio itself gives the value that if I1 is higher, definitely, if I is higher, definitely V will be low. V is higher, definitely I will be low. So the V is high, so definitely I will be low. Suppose you do this test for the LV side and you have to apply rated current. It may be 10, 20 or 30 nearly ampere range you have to apply. Because in the LV side current will be very high. So applying rated current in the LV side is difficult than applying rated current in the high voltage side. That is the meaning, or that is why we have to perform this short circuit test on what? HV side. This is a question. This is a question in your Viva or examination. No? Viva or objective type examination. You may expect a question like this. Why we have to connect, or in interview also, why we have to do SSC test on high voltage side? The answer is, if you do the HP test on high voltage side, on high voltage test or SSC test or short circuit test, we have to apply rated current. So if you do it for LV side, we have to apply large current in the LV side. But if you do it for HV side, we can apply a small current in the HV side. That is the rated current. That is a function. Plus. And how can we perform this test? Connections are made as shown in the figure. Slowly increase the value of V so that rated current will be flowing in the ammeter. The rated current will be simply, how can we calculate the rated current? Say an example. Suppose it is a 230 bar 115 volt transformer. Definitely, okay. Suppose it is a 1 kVA transformer. My dear, 1 kVA 230 bar 115 volt. Then what is the current in the primary? This high voltage side. What will be the current? The transformer ratio is nothing but this kVA rating of a transformer is nothing but, my dears, what is that? Or volt ampere rating of a transformer is nothing but V1 into I1, right? V1 into I1. So this I1 will be equal to what? Volt ampere is 1 kVA is 1000 volt ampere, right? 1000 divided by 230. So definitely 230 by 230, 4 point something ampere will be there. So that is the rated current regarding the high voltage side. But the low voltage side, see, divided by 115, it will be 8 ampere. Did you get the idea? Why we didn't perform SC test on what? LV side. Did you get the idea? The denominator will be 115 regarding the HV side, LV side. So 4 ampere only. So you have to increase the voltage in such a way that the ammeter will show a reading of 4 ampere. That is the rated current bus for this. So you will get the value of ISC. You will get the value of ISC. Bus. And you have to note the value of WSC also. Bus. Regarding the experimental did. You done. Okay. And our calculation side. You have WSC equal to VSC into ISC cos phi SSC. Is it clear, my dear? Or in other words, I can say that WSC is equal to ISC square into RSC. ISC square into RSC, or simply R. Simply R equivalent. ISC square into R equivalent. So from these, okay, you have two equations for active power now. One is VSC into ISC cos phi SSC, and other one is WSC equal to ISC square into R equivalent, where R equivalent is nothing but the same circuit can be represented like short. Am I correct? The same circuit can be equivalent resistance plus equivalent reactant referred to high voltage side plus VSC and ISC bus. So WSC can also be write like ISC square into R equivalent. From these, R equivalent will be equal to WSC divided by ISC square. Am I correct? And Z equivalent is nothing but VSC by ISC. Correct? So now you have R equivalent and Z equivalent. What is X equivalent? Root of Z equivalent square minus R equivalent square. Now you have Z equivalent also. So you have the values of R equivalent, Z equivalent and X equivalent. You have the value of no load power factor, full load power factor cos phi SC also, cos phi XC also. Bus. You have R equivalent, that is the resistance regarding to any side. If you are performing high voltage and no high voltage. If you have to find the low voltage segment, you have to convert all this to low voltage bus. Okay. So that's all about the SC test. That's all about the SC test. Okay. We will do a problem so that the idea will be more clear. Okay. So can I rub this? My dear? Can I rub this? Okay. Let's do a problem regarding this OC and SC test so that you will get more idea. Okay, more and more idea. Write a question, my dear. Write a question. A single phase, 250 volt bar 500 volt. 250 bar 500 volt. Transformer gave the following result. OC test 250 volt, 1 ampere, 80 watt. And the next SC test. The parameters are 20 volt, 12 ampere, 100 watt. On LV side. This is for OC test is done on what side you are doing OC test? LV side, and this is on HV side, correct? This is on HV side. Calculate the circuit constants. Question is calculate the circuit constant values. Calculate the circuit constant. Can we do? So first we can focus on OC test. First we can focus on OC test. Okay. What are the parameters here? What are the parameters here? V1 is equal to what, my dears? 250 volt, correct? And I0, because OC test you are named as I0, it is 1 ampere. And W0 is given as 80, correct? Am I correct? And it is doing all on LV side, okay. So it will become, ideas, it will become, so how can we proceed with? W0 is nothing but, what is that? W0 is nothing but V1 into I0 cos phi 0, correct? And what is cos phi 0 here? W0, that is 80 divided by V1 is nothing but 250. If you solve for this, you will get a value of cos phi 0 as, you can solve this in the examination, no? Direct cancelling type or easy angle type of question will be there. But now it is a random example. So cos phi 0 you will get like 0.32. In the examination, there will not be any troubling value, right? There will not be any troubling value. The value will be directly cut type, or suppose you will give definitely cos phi 0 is equal to 1 by 2. So definitely you can say like 60 degree. Correct? Cos 50 0 will be 0.5 you can directly like. So now it is 0.32. Okay, it's a random value, that's fine. So if you have the value of cos phi 0, what is IW? IW is nothing but, my dears, I0 cos phi 0, correct? I0 you have 1 into cos phi 0, 0.32. So it will be 0.32 ampere. What is IM, my dears? What is IM? What is IM? I0 sin phi 0 or root of I0 square minus IW square. That also a way for finding. If you do this, you will get a value of IM as 0.947. IM. So in the examination, you will definitely have a simple type, cancelling type. Need not to worry. So that's all about IW and IM. So the remaining parameter RW will be what, my dear? RW. It is nothing but V1 divided by IW, correct? So V1 is given as 250 by IW is given as 0.32. So RW we will get 781. And what is RM, my dears? What is RM? Not RM, it is XM, right? XM. What is XM? V1 divided by IM, correct? It is again 250 divided by, what is IM here? 0.947. So XM will be equal to what? XM will be equal to, you will get like 264 ohm. So that's all about from the OC test. So from the OC test you got no load power factor, no load, IW, IM, RW, RM. All the shunt parameter you got and the no load loss or iron loss from wattmeter, that also. That is the iron loss. 80 watt is the iron loss bus. So in the examination, you may not expect as a big question, but a small part of the question will be asked. A small part of the question will be asked. Okay. So that all from the OC test. Next we have to focus on SC test. Next we have to focus on, my dears, SC test. Okay. So this OC test is done on LV side, right? And SC test is on high voltage side or HV side. So we have VSC is equal to what, my dear? VSC is equal to what? It is nothing but 20 volt, right? 20 volt. This short circuit voltage is referring to HV side, my dear, HV side. Open circuit test, we calculated all these parameters with respect to LV side, right? So better to convert the side parameter to LV side parameter. That is the thing you have to do now. Did you get my point? See, this OC test you did all regarding the LV side, right? That means you calculate this IW, IM, RW, RM, all regarding LV side you calculated, right? So you have to do the SC test also regarding the LV side. Then only the parameter will not be changed or altered. The parameter will be correct. Suppose you calculate it for HV side, means finally you have to convert from this HV to LV side. Then only you can represent the transformer as simply R equivalent plus J into X equivalent. For doing that, you need to convert any side to high voltage or low voltage to any one of the common side. Any one common side you have to convert. So let me convert. This is to LV side, because I already did for LV side. So I have to convert the HV side parameter to LV also. So actually V2SC is 20 volt. Actually what? V2SC is equal to 20 volt. That means it is done on the high voltage side. So high voltage side parameter represented by V2, I2, R2, etc., etc. So this is actually V2SC is 20 volt is high voltage side. So what will be the low voltage side equivalent V1SC? How can we find that? The old value into to what you are going. You are going to low voltage side. So N1 by N2 bus. N1 by N2 is also equal to what? V1 by V2. So it is nothing but 20 into V1 by V2. V1 is 250 and V2 is 500. So it will be what? 10 volt. 10 volt. So now you got this parameter regarding the primary side was okay. And similarly, so the current also you have, no? Current also. You got this current as ISC is equal to what, my dear? ISC is equal to what? It is 12 ampere, right? It is actually the secondary current. If you want to convert it to primary, then what we will do? This is actually I2SC. If you want to find the current regarding the primary side, I1SC will be equal to old current into opposite to where you go. Opposite to where you mean reciprocal to where you go. I am going to N2, so the reciprocal, I am going to N1, so the reciprocal will be N2 by N1 in regarding current. So it will become 12 into what, my dear? It is 500 divided by 250. So it is simply I1S is equal to 24 ampere. I1 is equal to 24 ampere. Okay. So the full load copper loss, the full load PCU full load copper loss, it is nothing but 80 watt. Either it may be equal to I equivalent 1 square into R equivalent 1 or RE1, simply RE1, my dear, simply RE1, or which is equal to, I already said, I1 square into RE1 or I2 square into RE2. I2 square into RE2. I am preferring this equation I1 square into RE1 because I converted all these to LV side. This is already in LV side. This I have to convert it to LV side already. The P1SC and I1SC is nothing but the current regarding the LV side. So I can write like this I1 square into or I1SC square into RE1 equal to 80, or what is I1SC square? 24 square into R equivalent 1 is equal to 80, so that R equivalent 1 will be equal to 80 divided by 24 square. 80 divided by 24 square. No, it is 100. Sorry, my dear, it is 100, right? SC test full load copper loss is nothing but 100. So it is 100. It is 100, my dear. Sorry. So 100 divided by 24 square. What is 100 divided by 24? You will get an answer like 0.1736. You will get like so you got this RE1 and what will be ZE1? That is the equivalent impedance referred to primary. What will be that? V1 SC divided by I1 SC, correct? V1 SC divided by I1 SC. V1 SC is nothing but 10 divided by I1 is nothing but 24, right? So it will be give you the answer like 0.417. 0.417 ohm. If you have the value Z equivalent, then what will be X equivalent? It will be, what is that? Z equivalent square minus R equivalent square, right? Or RE1 square. ZE1 you may represent like ZE1. That is correct. ZE1 na? So ZE1, XE1 will be equal to ZE1 square minus RE1 square, and it will give you the value of XE1 is equal to 0.379 ohm. 0.379 ohm. Bus. 0.379 ohm. Simply you have to square this and subtract from RE1. Okay. So if you don't convert this, you will not get an equivalent side resistance or reactance. That is the purpose of doing this conversion. If you directly do this, no. If you directly do this, you will not get an equivalent circuit like this. You will not assume this circuit if you don't do this conversion. You can't assume this circuit XE1. This is equivalent circuit, right? You can't assume this circuit unless you do this conversion. That is why we have to convert this into standard values. Standard values. Okay, what is the time now? So that's all for today, my dears. Okay, that's all for today, my dears. We will meet on next class. Okay, so until then, bye. And one more thing, normally these type of problematic classes, no, may you feel maybe sleepy. I know that you may feel sleepy. I also feel the same thing. I actually slept during my classes when I was a BTech student. In the front bench, I slept in front of my sir like this. Okay, for machines, same machines. That sir was brilliant. The sir actually he was a genius. But no, after lunch hour normally, after we take a very good meal, definitely, even though it is pakka comedy in front of you, you may feel sleepy. That's the nature of our body. We can't do anything. So my suggestion is that either you want to see my classes on the morning itself. That's my one of the trick to override of sleep. Okay, that's my one tip to you. Please see, soon after you brush and you have a tea, you had a tea. Soon after you have to see my classes. Okay, and something you have to study by simply walking. No, that topic you may choose when you feel sleepy. When you feel sleep, take a book and some subject there will be you have to read and walk like this. You may choose that subject at that time, so that walking time definitely sleep will not be there. Am I clear? So these type of subject, machines and all, you have to sit and you have to take note and you have to study. So this time definitely you may feel or you fall asleep. I know that. So for that, please take care of this. That means you have to study this subject as soon as you wake up. As soon as you wake up, or after a good tea, you can take this subject and you can study. Never study this subject after lunch. Never study this subject late night. These two time, it's very danger time for theoretical subject. Even though it is quite interesting, it's very deep concept. You can't bear this. Definitely you will fall asleep. So it's my request. Okay. So that's I want to told you. That one I want to told you. And next thing, my dear, yes, regarding the sharing, you have to share this to your friends. I continuously saying the same thing. You have to share to your friends, because this is definitely this will boost their level. I know that. Definitely this will boost their level. Okay, that guarantee I can give you. My classes definitely boost your level. I can't guarantee that. Okay, definitely you will crack your exam, definitely you will get job. I can't say that, because in state PSC there will be nearly 1000 vacancies will be there. If you suppose my classes, you may see my classes will be seen by 1 lakh, suppose 1 lakh student. I can't guarantee that these 1 lakh student will get a job. No, I can't guarantee. I can guarantee one thing. These things will definitely boost your confidence level. These things will be definitely boost your knowledge level. That I can guarantee. That only I can guarantee. Rest guarantees now. Join our Telegram channel, join our study group, and join or take our discount offer and join this group and that group. No, many online platforms are there. They won't let you to, they can't guarantee that you will get a job. To get a job is 20% in SAR side and 80% in your side. You have to work hard. You have to work a lot for that. SAR or a teacher will definitely give you a basic or foundation. This basic, no, OC and SC. You will get a peripheral idea on OC and SC test. You have to do more number of problems. You have to know, solve many objectives and all. Then only you will be thorough. You will be firm in your subject. Otherwise, it's waste. It's a waste of time. So my request is, so these are the things you have to take care. Okay. So let's meet again tomorrow. Bye.